All right, so I think now we can begin. So today we're going to continue the thermodynamics unit. We're going to continue our thermodynamics overview. This is part 2. So as a review, so last time we were thinking about basic terms and definitions, right? We were thinking what is system, what is boundary, what is the surroundings, and then key state variables as well. We also talked about properties, processes. We really introduced a lot of vocabulary last time. So we made the vocabulary activity, which we sent to you guys via email. So you guys can try out that activity and email it to bchsphysics@gmail.com. We also talked about like heat and how work is pressure times volume in thermodynamics. We talked about ideal gas law, PV equals to nRT. And we also begun to talk about the first law of thermodynamics. There's a bit of a typo on this slide. This is supposed to be a delta U over here. We put an H here by mistake. So we corrected that in the review slide. So now we'll review first law of thermodynamics. And so the first law of thermodynamics is that energy is neither created nor destroyed, but can only be transferred from one form to another. Right here you can see on the slide, it just loaded up. And so the internal energy remains constant unless transferred via heat or work, is what the second equation is saying. The first equation is just definition of internal energy. It's kinetic energy plus potential energy. And the second equation is what this line here is saying. Internal energy is constant unless transferred via the heat, which is Q, or the work, which is W. So change in internal energy is heat plus work. And in an ideal gas, there are like no intermolecular forces, right? So there's no potential energy. So this PE term will cancel out for ideal gas.
So an application of the heat transfer can be seen this toy. So here's a perpetual bird water feeding toy. It has the illusion of being perpetual because it will keep oscillating forward and back, and sometimes it will dip into the water. So that's actually the key to solving this perpetual state. Is not because it's taking the water vapor, the fact from water that water is keep vaporizing from the cup, and when it vaporizes, it will cool down the temperature in the bird's head. As you know, when water turns into gas, it needs more energy, and that comes from the lowering temperature in the bird's head. So the bird's it's filled with a liquid that is easily turned into gas. So as the temperature condenses in the head, the gas will turn back into liquid and it will fill back into the bottom of the bird. So that's how it's keep oscillating and sometimes dip into water, because when the head is light, it will stand up, and when the liquid from the bottom then vaporize into gas, it will dip back down. So this is how it's keep bouncing backwards and forwards. And this is taken from an awesome video on YouTube, and you guys can watch it, and we will regularly update our B clubs. It's haven't been done in a while, and so there you can find the video. It's a very cool one on thermodynamics.
All right, yeah, we will update that so that you can check out that video. So next we have enthalpy, which is the net heat content of a system. It's defined to be the sum of the internal energy plus pressure times the volume. And under isobaric conditions, if you remember, isobaric conditions is like the same pressure, right? So we have that the delta H, the change in the enthalpy, is equal to Q sub P here. And then we have the change in the internal energy is equal to Q sub V here. And so if you have like a negative enthalpy, then that's exothermic, and a positive enthalpy is endothermic. So we're going to elaborate a little bit on this. So first we have some key terms. We have the idea of a reversible process, which is going so slowly that with infinitesimal change, you can actually retract it to its initial state. So both the system and surroundings revert. This is a completely theoretical process due to a concept called entropy, which we'll discuss a bit later. And there's also this idea of quasi-static state, which is just a state in which the system is in equilibrium with the surroundings. Next, we're going to talk about the unit of Kelvin. And so kinetic energy, there's a key idea in thermodynamics that kinetic energy depends on temperature. It's K equals, the Ke equals to 3/2 times K times T, where K is the Boltzmann constant. But what you need to know is that the kinetic energy is directly proportional to the temperature, right? And then temperature is also directly proportional to the kinetic energy, right? So if we have like 100 degrees Celsius, right, that's not necessarily 100 times hotter or like 100 times more kinetic energy than 1 degree Celsius, right? So scientists wanted something a little bit more absolute. And so that's where the Kelvin comes in, right? They were able to find like the temperature in which the atom has no kinetic energy, which is called absolute zero temperature. And that is 0 degrees Kelvin, which is this negative 273.15 degrees Celsius, right? So Kelvin is the base unit for temperature. Right, so whenever you define a scale, you need to define where 0 is basically. And so the conversion between Kelvin and Celsius involves adding and subtracting 273.15, right? So 0 degrees Kelvin, we add 273.15 to convert to Celsius, right? So for any temperature in Kelvin, you can just add 273.15. And then to go from Celsius to Kelvin, you subtract 273.15. So next we have a few key equations. We'll take it a little bit slow with these equations. First, let's talk about heat capacity equation. So C right here is the heat to raise temperature of the system by 1 degree Kelvin, right? So it's defined to be Q over delta T. And so here you have below it is the molar heat capacity equation right here. This C sub m equals Q times delta T times Q divided by N over delta T. So we just took this first equation and we divided by N, which is the number of moles, right? So now you can raise the temperature of 1 mole by 1 degree Kelvin, right? Because we just divided out the number of moles between C and C sub m, right? Next, we have C sub P, which is basically the isobaric condition right there. That's constant pressure. So C sub P is equal to the heat at constant pressure divided by N times delta T, right? And then C sub V is also Q sub V divided by N times delta T, right? It's basically the same formula under the constant pressure and constant volume conditions, right? And then we just substitute what we learned in the enthalpy slide, right? That change in the enthalpy is equal to the heat at isobaric condition, and change in the internal energy is also equal to heat in the isochoric or same volume condition. And so we just substitute that right into here, right? We say delta H is Q sub P, and then we multiply out N delta T on both sides for these equations, to get these equations. We mute the D10 to proceed. Okay. So we have these equations. After we multiply the N times delta T on both sides.
So if we held both pressure and volume constant, so a very important concept we can get from heat capacity is that for some matter, if we raise the same temperature, and some matter will absorb more heat than others. And this is how engineers decide what's a coolant or like agent they use when they want to transfer heat out of the system to cool the system. So some important places we use them are car engines or any internal combustion engines, and refrigerators in this case. So because you need to move matter to transfer heat out and basically expose them to temperature difference so they can absorb heat or release them. You can see engineers use air. So that's the case in the car engine radiator. It basically is something that combines with fan and brings in air. And they also use this green liquid. Maybe you have seen it, and you add it, and it has relatively large ideal heat capacity. so it can bring out heat to the atmosphere as it circulates in the car's cooling system. It's also something that's used in refrigerator, and so HFC dash 134A is a product that is a coolant that's most popular right now. They used to use chlorofluorocarbon, but it's harmful to the environment if it's released into the atmosphere, so they changed it. So yeah, and water is usually a great cooling agent because it has a large heat capacity and is very accessible and it's not harmful to the environment. So it's probably the most common, one of the most common coolants out there. And adding chemicals will allow you to change the heat capacity and change property of your coolants. And sometimes we also use oil, and air is also very popular because it's both accessible and you can make it transfer very easy. So we have, yeah, next page we have a picture of the engine. This is a picture of the car engine, and you can see it both brings in cool air from the outside, and it has water flow to cool down the engine. And this is one from a plane engine. So the air is both used for propulsion and cooling down. And there are some very awesome design out there. If you just search up plane engines in YouTube, you can understand it more in depth. So basically they have some developed some different designs over the years. And so they basically air is a very interesting thing here because it has very different usage, like two different usages mainly, and they change the design so they can have more airspeed, so they are increasing the basically increasing the engine efficiency over the years with different designs.
All right, now we're going to discuss the interesting concept of entropy. Entropy is the degree of randomness or molecular disorder in the system, right? So, and conceptually, the more entropy the object has, the harder it is to do work. So formally, we define change in entropy to be the heat reversible over the temperature, right? But the scientist Boltzmann came up with another definition for entropy as well, right? And it's the measure of the number of possible microscopic arrangements. And so this omega right here is actually the number of microscopic arrangements. And then K sub B is just the Boltzmann constant, which is the ratio of universal gas constant and the Avogadro's number. But for now, you can think of it as just a constant, a key constant in thermodynamics. And so entropy has to deal like a lot with randomness and molecular disorder, right? So to go from this idea of heat over temperature to that idea is basically Boltzmann's idea. And so the idea is that you have like a lot of different random configurations, right? And there are very few configurations with like order and stability, right? And so there's the idea that the universe is tending toward like chaos and disorder because of all these like so many different microscopic arrangements, right? But there's really only like a few of those arrangements in which you have system of order, right? In which you have like a solid, for example, right? So solid has like less entropy than liquid, which has less entropy than gas, right? And that has to do a little bit with the ordered configurations. It's a bit of a complicated idea, but it's still very fascinating. And that leads us directly to the second law of thermodynamics, which will tell you that in processes and chemical reactions, the entropy will always increase, right? If entropy will decrease, then in a system, then the entropy of surroundings will increase. Right? We talked about system, boundary, and surrounding. So if entropy in system decreases, And the entropy in the universe has to increase to compensate for that. And so the spontaneous process that runs on its own will be impossible with decrease in entropy. The entropy will always have to increase or stay constant at best, but it can never decrease, right? So we have an example of the ceiling fan. And we think about like the processes that cause the ceiling fan to work, right? So you have like a river running somewhere, right? And then that river will spin like a turbine, right? And then that's what's going to generate like electric power. That's the hydroelectric power. So you have electricity then. And then that electricity goes through like a bunch of circuits and then reaches your house, which will allow like the ceiling fan to spin. So the overall processes that is causing this actually allows for the entropy of the universe to increase, which is why your ceiling fan actually works. So as energy goes from one form to another, you have more that is wasted. You have some wasted energy or heat energy as you're converting between different types of energy. Is also a key principle of second law of thermodynamics. And it extends to the idea that heat flows from something hotter to something cooler, but it cannot flow the other way back, right? And so second law of thermodynamics ties a lot into like efficiency, right? Where you think about like an engine that has like 70% efficiency at best, right? That's where the second law of thermodynamics will come in. It's due to the second law. And so this is the mathematically what the second law is saying, that the change in the total entropy is equal to change in the entropy of the system plus change in entropy in surroundings, which is greater than zero. If you're writing stuff on a test, you can shorthand this, I guess.
So that second to last idea that heat flows from hotter matter to colder ones will lead us to this theory that is the heat death of the universe, or a big chill as it's more friendly. So this is a theory that conjectures that the universe will ultimately reach a thermostatic equilibrium, meaning that everywhere the temperature is the same, there's no temperature difference in the universe. And this way, entropy is the max. It's also when all the temperature even out by the entropy difference or the temperature difference. So in that case, the heat diagram below it would be even. So it is this theory is consistent with the fact that universe is expanding. So as the universe expands, it will eventually cool down and reach the equilibrium because um, because as it expands, there's more space out there, and basically what is called dark energy, it will um, it will takes up more percentage of the entire universe. So what's left, it'll be reaching the thermostatic equilibrium. So that means there's no free thermodynamic energy to do work, and without work, basically conceptually, there's no the entropy is at max because if you have entropy, you have to have the availability to do work, and that's also another a conceptual understanding of entropy.
Now we look at this concluding concept of Gibbs free energy. This is a little bit of additional information and that you might encounter if you take like AP chemistry or AP physics too. You can think about Gibbs free energy, which is just a parameter, right? It allows us to think about how spontaneous a process is from the system's perspective. And these are a few key formulas for Gibbs free energy, right? So change in Gibbs free energy is equal to negative temperature times the change in the total entropy. And in order for a process, this is for the isothermal and isobaric conditions as written on the side. For a process to be spontaneous, you need Gibbs free energy, the change in Gibbs free energy to be less than zero. And in isothermal conditions, so like non-isobaric, but just isothermal, we have that the change in Gibbs free energy is change in the enthalpy minus the temperature times the total entropy. So that is the concept behind Gibbs free energy. All right. So that will conclude our presentation for today. Are there any All right, so then if there are no questions, you can send your questions to vchsphysics@gmail.com, or you can ask your questions in the chat as well. I'm going to quickly pull up the vocabulary activity just to show you guys that real quick. All right, so this is the vocabulary activity. We encourage you guys to try this activity out and to email your responses to vchsphysics@gmail.com. And we're reviewing basically key ideas from the first unit, from the first lesson, right? Where we talked about all the different terms of vocabulary. And it can be very hard to like commit this like to memory, right? Like what does it mean when we're talking about isobaric process or isothermal process and all that, right? So in about a week, I'll share like the Quizlet for this. But for now, you guys can try out these questions in which we really clarify some of the vocabulary here. You guys can try this out, send your responses, and we'll send back like where you got it right, where you missed. Yeah, it's a good way to learn the vocabulary here. Different ideas, right? Different properties, processes. And so yeah, you can learn like all these different terms, concepts, and vocabulary, which is very important in thermodynamics. Really a lot of key concepts this unit. So yeah, we really do encourage you guys to try out the vocabulary activity to become fluent in a lot of the principles in thermodynamics.
Yeah, so please take some time, and then hope you're having a great day. And so yeah, have a great day and hope to see you next time. Bye. Thank you. Thank you, Rohan.
Thank you so much, Alan. Thank you, Alex.
All right, see you.